So our levers are considered to be force multipliers. And the English alone is going to tell us it, excuse me, my phone is, all right, it is a force multiplier. And what does a force multiplier do? It multiplies a force. Plain English, no set of complicated terms and terminology. All right, a lever is simply meant to increase the action, all right, of a force. All right, everybody. All right, so let's look at here. And a lever, not a lever, a lever is a simple machine, and it incorporates the principle of movement, as in it's plain straight. The most common example or explanation or um, demonstration and utilization of moments. And in a lever, there are three main sections to identify. We have the effort. This is where force is being applied. We have our pivot. Pivot is where our forces act from. And three, we have our load, where the force that is being moved. So what do we do with a lever? A lever is simply something that we use to lift an object. Yes, Karima. Yeah, I have a lot of all of that stuff. Yeah. All right. So these are three areas of our lever that we have to be able to identify. And let's see where we have our areas. We have our fulcrum or pivot, like any other um, moment system. We have the effort. The effort is the part that we push down on or that we apply force with. And the load is whatever we are lifting or what we are moving or opening and stuff. The key is to be able to identify where the pivot and forces are acting. So we have three classes of pivots, of levers. It's not necessarily something you all need to know for exam, but there are different types of levers because they look different. But when you think about them, it basically behaves the same way. So we have our first class of lever, which is plain straight out, easy to see where we have our pivot. We can see where our effort is, right? And we could see where our load is being lifted. Really simple, right? So we have the pivot in the middle, our input force or our effort, right? And then we have the output force being the load that we are trying to lift, move, cut, change, and whatnot. So an example here will be a pliers. You all try a pliers or scissors today. Pick up a scissors and look at it, and you're going to realize is scissors. I have no scissors on my table. Is scissors is a lever, an example of a lever. While because if you look at it here, there's always a little pin in the middle of your scissors. That is our pivot, our pivot, right? We are holding down on one side of that lever system to open and close, right? And then we have the cutting side, which is our output. So that is plain. It looks like it's basically like a double lever system. Okay. All right. The video not sure. All right. We have second class. This is where our pivot is not necessarily in the middle or kind of in the middle of our system. All right. If you look here, perfect example is a wheelbarrow. Now, wheelbarrow, if you have a wheelbarrow, for those of you all who have ever used the wheelbarrow, that's a horrible diagram or whatever, right? Your wheelbarrow, we know that the point at which a wheelbarrow goes up and down will be your wheel. It has the legs here, right? We don't use the legs to move our wheelbarrow. We don't use the legs to move it up or down. What we do, we lift it up and we hinge it, meaning the motion to go up. Let me take off this video. You're not seeing it. All right, the motion to go up and down is not recorded or is not recorded, is not seen in your right. Our pivot is usually where our things go up and down. Right? For a wheelbarrow, if this is our wheel, right? Our wheelbarrow is here and we could lift and drop our wheelbarrow depending on where you know, we angle it to the wheel. So our wheel ends up being our pivot or fulcrum. And where do we lift in a wheelbarrow? We lift at the handle, so that's our effort. And our load is going to act from the middle of our wheelbarrow, act downwards, and that's going to be our load. So you see how even though it is a lever system, it doesn't necessarily look like a traditional moment seesaw kind of thing. Third class, we have, here it is a little different. We have, like, say, example for your arm. Our arm is a lever system. And what is our pivot? What bends on our arm? Your elbow. This is what is bending, right? It's in a hinge, and it's a kind of, yeah, it's a hinge joint. So it moves up and down, right? If we have to lift something, which part are we going to lift it with? This part of our arm, this part of our arm, or with our hand? We're going to lift it with our hand, right? So obviously our hand is going to be our load because that is what we are lifting. So if you have to pick up something pretty heavy, let me see if I can get it, right? If I have to lift up something, right? This is acting down, so you are lifting this up. And what is causing our arm to pull up something is going to be our muscle in our upper arm. So this is where you have our upper arm, and our forearm is where we are pulling up something. So the distances, not the distance, the locations of our forces are a little different in our different types of levers. Whose mic is on? I will see you now. Okay, it's gone. So for homework, it's not homework to submit, but it's homework that you need to know, because this type of question comes both in your long paper and in your multiple choice, where you have to be able to look at a diagram and, from your knowledge on how things work, be able to identify where your pivot is, where your effort is, and where your load is. So I want you to get 10 examples. Yes, you can get 10 examples because we have Google. We could find, if you didn't know about it, you could say, oh, I didn't know that was a lever. So get 10 examples of everyday levers, right? Levers in everyday usage. You can get up to 10. And what I want you to do, you can either draw or print out those 10 examples and identify where the pivot is, where the load is, and where the effort is. Please, 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 folks, don't just go and print a straight document where you all made no effort to learn anything. I know that sounds like the easy way out, but please, we have to learn for exams. And the best way we learn for exam is we apply our actual knowledge to what we see in front of us. Is that clear with everyone? Yeah? All right, so this is for homework for you to do. If you want to do it and don't want to do it, that's up to you. You're nearly a young adult. Be a little responsible. All right, so moving on, half an hour left. All right, this will give us enough time to deal with our next lab, which is this is probably the most common AI lab done across schools in the entire world, honestly. So I have here, I want to determine the acceleration due to gravity using a simple pendulum. Now, what is a simple pendulum? A simple pendulum is simply an object that undergoes regular back and forth motion. This, let me see, is a simple pendulum, meaning if I rock it back and forth, it's going to go back and forth. Let me stop share so you all can see that better. All right. No, don't see my upstairs. All right. So if this is our pivot, all right, our pivot right now is in rest position. But if I displace it a little bit, it's going to have a generally relatively even back and fro motion, kind of like the hands of a clock or something, right? This is a simple pendulum. That's all it does. And we can use the motion of the simple pendulum to calculate the value of G. You would not believe how simple this is. This simple thing going back and forth like this and recording how long it takes to go back and forth is going to tell us what the value of G is, but we have certain rules to use. All right, so the first rule we had, remember I had started you all up with this last day, right? First thing we have to do, we have to measure our length of our pendulum from wherever we are suspending it. Remember I told you to probably wrap it around something, clamp it to something, use a paper clip, use a clothes clip. Clothes clip is a good idea. And you are going to be measuring the length of your pendulum from wherever you are suspending it to the middle of your pendulum. Right? We don't want it at the bottom. We don't want it at the top. You're going to estimate where the middle of the pendulum is, and you're going to take the length of your pendulum. So what you're going to be doing, you're going to be using different lengths. I have in the handout what lengths we are using, and you're going to displace it. Displace means to move from rest position. Question, Michelle?
I'm not seeing the handout.
Because you're in live video right now,
No, the handout that you give.
I posted it in the Google Classroom just now. All right, so what you're going to do, rest position is where it is just here. Now, my fan is blowing, so it's going to be, as you can see, all right? I want to displace it through a small angle. Displace it through a small angle means I want to just move it a small amount and let it go back and forth. Everybody, it has to go back and forth, nice and smooth in a small angle. I don't want you to come and do this. Because imagine if this was in school, we're using a steel bulb, this is going to hit somebody. This is going to be wrong. Because of the way the mathematics for this works out, you need to displace it through a small angle. All right, don't worry. This looks like a small amount and you wouldn't be able to take the time. It's going to keep working because we're starting with 50 centimeters, which is like from here to, pretty long, right? 50 centimeters and not in the camera, right? So we are going to be taking times for oscillations. Now, what is an oscillation? An oscillation, let me see if I can get it. I can't get my camera. Right. An oscillation is the time it takes to go forward, to start from one point, go away from you, and then come back to you. That is one oscillation. So let's see. This is one oscillation, forward and back. Right? Forward and back. That is one oscillation. So we are going to be taking times of multiple oscillations. Why are we taking times of multiple oscillations? To get a time when it does this, it's going to be pretty hard. So what we're going to do, we're going to let it swing several times and take the time it takes to swing several times. So let's see, we're going to try it for, say, 10 oscillations. Remember, when we count, we start from 0 because it has to go forward and back to be one oscillation, right? So let's see, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You take the time for it to do multiple oscillations. And because it takes so long to do multiple oscillations, you get a much more accurate reading of the time it takes to do one oscillation. All right? Everybody, that makes any sense? You want me to go through it again? Nobody? People fall asleep? You good? Right. So remember, for an oscillation, where is the camera? Right? What is our oscillation is? It's simply the motion. The best way to look is to look at when it is moving closer to you. All right, remember this is going to be attached to something and this is going to be flowing free. I have this oscillating through a very large angle for demonstration purposes. But if this is our lab, we just want to move it a little bit. And don't worry, it's going to oscillate enough to get readings. Don't say you have missed, it doesn't look like it's going to work. So I'm going to start from quite here and do stupidity. This is stupidity. Right? Because the maths does not work when it does a big angle like this. It's not going to work out. So what you're going to do, you're going to see where it hangs in rest position. You're going to displace it through a small angle. I'm going to show you how to find a small angle. Small angle, and you let it oscillate. Now, the oscillation here has to be nice and smooth, meaning it's going back and forth in one straight line like this. right? And you can see actually going back and forth in one straight line like this. If your pendulum is going back and forth in one nice straight line, then that means you can take your readings. If it's going to be start doing this, y'all, that's a circle. You don't want it moving in a circle. You don't want that happening. You want your pendulum to be going back and forth in a nice straight line. So if you have to release it several times and let it make a nice motion, do that. So yeah, this looks good. All right, nice smooth motion. So when you realize your pendulum has a nice smooth motion, then you start taking your time. Do not do this, release it, and then start your stopwatch on your phone. Don't do that. You have to release it first. Make sure that you're getting a nice smooth motion as you realize this one is moving nice and smooth in one line. Then you decide when it comes closest to you, you start your stopwatch. You have to let it swing once to be 1, twice to be 2. You do not start counting at 1 because then you're going to miss 1. So let's see. If you're going to be doing this, I'm going to let it swing. All right, I'm going to start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Stop. All right, so you'll be taking the time for 20 oscillations every time for this lab. So you all don't let it do this. All right, you see if you're doing this kind of back and forth in all kind of angles, you're doing the lab wrong. Not that say you are doing the lab wrong, you released it wrong or it just doing some kind of dancing motion. We don't want that. We want a nice, smooth, back and forward motion. Everybody clear with that, right? So that's to tell you, my bob, I just used, it's plasticine, the same plasticine I told you all to buy. And I think in the middle of my bob is nothing. I made my bob from a piece of plasticine. So let's take it and mold it around the edge of your thread, right? Get a nice, pretty even bowl, right? And you get your pendulum back. It's heavy enough to do the motion because sometimes we use a little tiny, tiny little, this tiny bob. And this is clearly much heavier than that. So it's going to work out. So let's go back to the handout. Any questions right now before you go back to the handout? Are we okay so far? I'll look in. I see no hands up. Nothing. All right, we're going good. Share screen. So in the school, if you were doing this lab in school, we would have a retort stand, right? This is our retort stand, right? And our retort stand is going to be holding something that's going to hold our bob. We are going to have to think about something. Remember, I gave you ideas. You can put it on the end of a ruler. You could tie it on a piece of wood. You could tie it on a pole. Get somewhere where you can swing your pendulum without anything hitting it and without any breeze affecting it. Clearly, I have the fan on, so that's not right. So in school, we would have a retort stand, a clamp, a rubber bong. A rubber bong is just something that looks like this, right? With a pin sticking out to hold our bob or pendulum. And what we have there, and it's going to be hanging off the side of the table because we are starting with 50 centimeters length of pendulum, and we're going to go down to a meter. So we need somewhere high enough, right? Pretty much higher than your table to swing our stuff without it hitting anywhere. Now, if your bob hits the ground, you're clearly not high enough. A little bit of common sense. So say, Miss, it was hitting the ground. I will have to write down your name and clouch you next to him. Right? I am telling you, just make sure if we're going to be swinging something, you don't want it to hit the ground, you don't want it to hit the side of the table, you don't want it hitting yourself. Don't do that, eh? Don't. So we're going to have it running, swinging back and forth. And what we want to do, we want to go and use an angle of about 10 degrees. Now, how are we going to find an angle of 10 degrees? We use a protractor, right? Really nice and simple. So this is what you're going to do. If we have All right, this is our pendulum. And we're going to get a protractor. We're just going to take our protractor. Let me see if I have a shape of a protractor. No, I don't. All right. So you're going to take your protractor. Right. You all know your protractor actually has a 0 in the middle. So you're just going to take your protractor, line it up where it is hanging. All right. And you're going to see, you're going to go, and so this is going to be 0 or 90. You're going to have to hang it, let it swing, hold your thread, and release it from 80 degrees. Right? And if it release it from 80 degrees, obviously you would have swung it through 10 degrees. So you're just going to hold it. You will see that you're pulling the thread 10 degrees, right? About 10 degrees, that can take about up to 15. But after that, your lab will not work out perfectly if you use a big angle. So use your protractor. So all you have to do is just hold your protractor up to where you're releasing it, or you can find some way to stick it. Right? Be a little ingenious. I would love to see how you all try this. Right? Pull the thread 10 degrees and you release it. And once you release it, make sure it has to have a nice smooth back and forward motion. Right? You want it to be going a really nice smooth back and forward motion. You don't want it to be doing this where it is making an S motion and wobbling all over the place. You're not going to get a correct answer. So sometimes you're going to have to do it several times to get a nice smooth motion. But as you go through the lab, you're going to realize how to release it. You're not throwing it, you're not flinging it, right? You're just holding it and releasing it, let it move under gravity, and it's going to get a nice smooth motion back and forth. So you can use a protractor, right, to find out your 10 degrees. This is up in the Moments handle that I just posted, so I put everything together. So let's see. The motion of a simple pendulum can be described by the equation of t is equal to 2 pi by the square root of L over G, where t is your periodic time. That's the time it takes to make one oscillation. Right? That is one oscillation is your periodic time. L is the length of your pendulum. Remember the length of your pendulum. You are taking the distance from where you hang your pendulum to the estimated middle of your bob, whatever your bob is. As I said, I just use plasticine on the end of a big, cord, which is too big. So we have our periodic time, the length of our pendulum, and g is the acceleration due to gravity. Now I didn't put this down in, but how do we manipulate this equation? A little tip for an extra bonus mark that's going to go towards your bonus marks for the term, not your SBA mark, but your term mark. When I manipulate this equation and I make G the subject of the formula, I'm going to get G is equal to 4 pi squared by L over T squared. If anybody wants to, if you're pretty okay with maths and do it on your own, don't go and ask somebody who's done physics before to show you, because I realize looking at some people physics labs, you have somebody helping you all. I can see when people are helping you all versus when you try it yourself. Helping is fine, but you have to learn to develop these skills on your own. Right? So if anybody can show me how we get from T to making G the subject of formula, so that means you have to go and square something and transpose and whatnot. If anybody can show me how you get this equation, all right, I'm going to give you a bonus mark that's going to add up to the rest of your term marks. Not an SBA mark. That's unfair. All right, so this is our equation. G, to find G, it's going to be 4 pi squared. All right, so it's going to be 4 multiplied by pi, multiplied by pi, multiplied by the L over T squared. Now, please, we are not using just L over T squared from any value. We're going to find this out in a certain way. We're going to come down. We have our method, we have our reading. So what is our method? All right, one, you're going to measure the length of your pendulum bob from the point of suspension to to the middle of your bob. Then you're going to displace your bob through a small angle, right? So it's going to be displaced through a small angle, and you're going to record the time for 20 oscillations. What is 20 oscillations? That is the time it takes, whoops. That is the time it takes to go, if you start here, that is the time it takes to go forward and back to you. That is what I call one oscillation. So you are going to let it swing 20 times back and forth. Take the time it takes to swing 20 times back and forth. I just did a demonstration for you all. So it's not like, you're taking the time of 1, writing it down, taking the time of 2, writing it. No, you're letting it swing 20 times and taking the time from start, let it swing 20, and then stop. Is everybody clear with that? We understand what I meant by 20 oscillations? If anybody, yeah, good. All right, so this is your rest position. That is where it will just hang without you pulling it. This is where you are going to start. You're going to pull it some small degree. Remember, you're using your protractor here, 0, 80 degrees. So you're going to pull it through 10 degrees, and then you're going to release it from this position, let it swing forward, and then it's going to come back to you, and that's going to be one oscillation. So that is one oscillation. So you're going to have to do this 20 times. And when it reaches the 20th time to you, you stop your stopwatch. So play with the stopwatch on your phones. Every single cell phone has a stopwatch on it. So finally, if you don't have a cell phone, you need to tell me. All right, or you can just borrow someone's cell phone. This lab takes about half an hour to do because we have to, as you realize, we have to try to make sure we get a nice smooth oscillation. We're not getting an oscillation not going back and forth, right? Like a little drunk, whatever. Okay, so you want nice and smooth back and forth oscillation. So let's see how to do our table of readings. So we are starting with 50 centimeters. L is going to be, this is L, not I, right? L is going to be 0.5 meters. 0.5 meters is 50 centimeters. So you're going to do 0.5, 0.6, 0.7, 0.8, 0.9, and 1 meter. So you're going to be doing 6 readings. And we are going to be taking 20T twice. So we're going to let it do the 20 oscillations once, take the time, and then I'm going to repeat that. So let's just do an example here on the board. All right, so suppose I get 14.10 seconds. Please, 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 all you. All right, everything we must use 2 decimal places for our readings and 2 decimal places for our calculations. Don't round it off to 1, but don't round it off to 0. You're going to get it very, very wrong. So I have, say I let it oscillate 20 times, I get 14.1 seconds to do 20 times. I stop my stopwatch, I start over my apparatus, let it swing again, let it get a nice comfortable swing, start my stopwatch, and I get, for my second oscillation, I get 14. Not 40, let's do a decimal. 4, 5. All right, so those are my 2 readings I'm going to get when I work out my oscillation times. Now I want to look here. If you see, I have 20T average. How do we find average of 2 numbers again?
I'll divide by 2.
You add the 2 numbers, you press equal, and then you divide by 2. Your calculator does not follow BODMAS. So please do not go in your calculator, say 14.10 plus 14.45, and then you hit divide by 2. You're not going to get it right because your calculator is going to assume you're doing this where you're just dividing the 14.45 by 2. So your calculator is not following BODMAS. So please, folks, work out the total of these 2 numbers. Somebody write now their calculator. Tell me the average of 14.1 and 14.45. Round it up to 2 decimal places.
Um, 14.28.
14.28. The actual answer is 14.275, but we want to round this up to 2 decimal places. And we know we round up a number when we're 5 and greater. So it's going to be 2, 8. So now I have 20t is 14.28. So if 20t is equal to 14.28, how am I going to find t? Anybody?
Divide 14
By 20.
by 20.
By 20. So we're going to divide the 14.28 by 20. All right, 14.28 divided by 20. And we're going to put our answer to 2 decimal places. And here I get 0.71. So that is t for this table. All right, as I said, I'm recording this so you all can look at it again. Make sure you're doing your calculations correct. And the last table here is t squared. So all we're going to be doing is squaring t. So you hit square on your calculator to 2 decimal places and you end up getting the actual value I get on the calculator is 0.509. Is this 2 decimal places? No. So I have to round up my last decimal place. So I'm going to get 0.51. And you're going to be doing that for the entire table. Now, looking at the really silly mistakes people made during the last lab, you are going to get successive larger times, meaning 15, 17, 20, 23, 25. It's not going to be that actual time, but you are going to get successively larger times for each length. So if you realize you are doing this and you get, and the 90 centimeters, you get 12.1. Something went wrong. All right, something went really wrong. Do it over again. You are supposed to get successively larger values for each reading. So if you realize this is where you don't just blind take values, you have to think a little bit and say, hey, wait a minute, that's not right.
Mrs.
Right?
Is how we get the value for the last column again?
You square t.
Oh, thank you.
You see this? Isn't this t squared is squaring your t value? All right, so that's what we have for there. All right, so again, little tip, you all are going to get successive larger values here. Same thing for t squared, this is going to get larger to the point where you're going to get 4 point something. All right, the last one you're supposed to get 3 point something or 4 point something. Nearly finished, so you are going to plot a graph of L versus T. All right, so first thing you're going to do, you're going to plot a graph of L versus T squared. All right, what is going to be on the X here and what is going to be on the Y?
L is Y, T squared.
L is Y, right. Now you all notice that we started from 0.5. If you want to cut your graph and start at 0.5, that is fine. But to plot up to 1 on your y-axis is really easy. You can go up by, a really nice decimal point. I'm not giving it to you. All right, so your choice. If you want to cut your graph and start at 0.5, that is fine, but you have to make sure that you cover plenty of the page. Or if you want, start from 0, don't cut your graph, right? And you can go up the graph. It will fit, so don't worry about it. Your choice to what you're putting on your axes. So you're going to do that, 1. 2, you're going to calculate your gradient. All right, so you're calculating your gradient. 3, to calculate g, g is 4 pi squared by L over t squared. L over t squared is equal to your gradient. So all you have to do now is just multiply 4 pi squared by your gradient answer. And you are going to get G. Please do not forget your units. Just to give you a little tip, on average, depending on what you use and how accurate you are, your gradient is usually anywhere between 0.20 to 0.3, with the ideal value being 0.25. All right, that is the ideal point. No matter what apparatus you use, you should get the gradient to be about 0.25 or a little above 0.25. All right, so don't worry about it. What I want you all to do, I'm going to put up the dates and stuff in the Google Classroom, so I have to set the assignment. But I'm going to put up for you, you have until Sunday. You all can start this today. No, you have until Monday to submit, to do your calculations and your graph. I just want to see the calculations and graph to make sure that you're going okay. So you're going to take a photo of it, right? And attach it to, well, if you take a photo, just a photo, you can put up a photo alone. If you want to send it, you must send it in Word, not in a PDF. If you send anything to me in a PDF, I'm just going to give you back a mark and no corrections. I'm telling you all, I've told you all this numerous amount of times. Send your work in a Word document. So that way, you see like how I draw on the screen here, I can easily mark it on the screen. If it's on the PDF, I cannot mark on the screen with a PDF. All right, so you all, let's just follow this again. You are going to take the length of your pendulum. You're starting with 50 centimeters. You're going to take the time it takes to oscillate 20 times twice. Remember I said for you all, don't just release it and start your stopwatch. It has to swing really nice to give you a nice back and forth motion. As you can tell, this one is swinging around in a circle. That's not working. You want it to have a nice back and forth motion. And when you realize it has a nice back and forth motion, you start your stopwatch and you let it swing once, come back to you before you say one, where it has to make one full oscillation before you can say one. All right, so you're letting it do 20 times. You're taking the time for 20 oscillations twice. Then we are going to find our average of those 2 oscillations. Then we're going to find T. How did we find T? We divided by 20. And then we're going to find T squared. So you're going to be squaring whatever you get in the T column, then square that value. So an example, if T was 2, squaring it, you're going to get 4. All right, very simple. Then you are plotting a graph of L versus T squared. You are calculating the gradient of your graph. Then you are going to be finding G. And how do you find the acceleration due to gravity? It's going to be 4 by pi squared by your gradient. Everybody? All right, that is what we're going to be doing. I'm going to put up the rest of the instructions in the assignment. So I'm posting the assignment right after the class because we're finished now. So I'm going to post the rest of the assignment in the Google Classroom. All right, and I will post up the time that I want you all to send me in by, to send me the calculations and graphs, so that way I can check and make sure that you're going okay. If you do the lab today and you send it to me tonight, I should check it up one time. All right, because I'm going to try to have these marked immediately, or at least to check it. Please send it to me in the Google Classroom or in my Gmail. Do not send it to me on the phone because I don't know where the phone is right now. I think I'm on my bed. Right? So send it to there. So at least I can check it. When I have to send it to my phone, I have to send it to my next account and then send it to the computer. It's annoying. All right, so please, folks, send your work to me. Send a very nice, clear photo so I can see that you all are going okay. All right. No, send me the table too. Send me the table, the graph, and the calculations. But you should get for your gradient anywhere between 0.2 and 0.3. 0.3 is too large. 0.2 is too small. Right? Ideally, you want 0.25. Don't ratchet, right? And give me not 0.25. Okay? And work out your stuff. Your lab will be due next week, Wednesday. So the earlier you send in me in your calculations and whatnot, the earlier you can send me in the full write-up. I'm going to put all the instructions and everything in the write-up in the Google Classroom for the assignment just now. So if anybody has any other questions, we're going to wrap up there now. Any questions, anybody? No questions. All right. So yes, I know it is Friday and I gave you all some work to do, but you can have some fun with it. Some students enjoy this lab, right? So you can have fun. If you want to have a partner, you can have a partner. You don't necessarily need a partner because this is one of the labs that can come for a lab exam, and you do all the lab exams by yourself if you have to write a lab exam. So folks, have a good weekend. I look forward to seeing your work as soon as possible and not last minute. So see if you can work on that today if you have, if you have some free time today, right? And get it done. So everybody, bye-bye. See you next week.
Miss, enjoy your weekend.
You too.
Bye, Miss.
Bye-bye.